So let's begin this video by talking about the concept of a mole. So imagine an atom. An atom is a very, very small unit. You cannot see it, and it's so tiny. So what chemists did is they invented the concept of a mole, which basically means they took a whole bunch of atoms. That's a very, very large amount of atoms, and they smushed them together and they created a package. And that package is called a mole. Now the question is, how many atoms are in one mole? Turns out it's a very big number. So 1 mole is equal to 6.02. In some books it will say 6.022. So you can take that times 10 to the power 23 units. So why do we say units? Because units could be atoms, it could be molecules, could be ions, could be essentially anything. But since we're learning chemistry, we will typically use either atoms, molecules, or ions. Okay, so that's how many units. So now it turns out, because the atom is so small, you need a huge number to basically make it a significant quantity. So let's try to understand what this huge number means. So it turns out, if I take these many units, so 6.022 times 10 to the 23 units of carbon. So let's say I take these many carbon atoms and I weigh them. They will weigh 12.01 grams. So see, this is a quantity that you can see. Okay, you can see, you can feel, you can touch. So it turns out, if you weigh out 12.01 grams of carbon atoms, turns out that 12.01 grams would contain these many carbon atoms. If you do the same thing for hydrogen, that would be equal to 1.01 grams. Okay, you do the same thing for oxygen. So we can say for oxygen, we can say 1 mole of oxygen is equal to 16.00 grams, which is equal to these many atoms of oxygen. Okay, so you might be thinking, well, what is this number called? So it turns out this number was actually coined by a scientist named Avogadro. Therefore, this number is named after that scientist. So it's called Avogadro's number. So Avogadro's number of units is equal to 1 mole. Okay, Avogadro's number of carbon atoms would be equal to 12.01 grams. Avogadro's number of hydrogen atoms would be equal to 1.01 grams, and so on. And so you might be thinking, well, how would you know, since the number is the same, but how would you know how many grams they weigh unless you weigh them yourself? Well, it turns out you can look at the periodic table, and when you look at the periodic table, you'll find something called the atomic mass of each element. So for carbon, you will find the atomic mass of carbon. I'll just box this. That number is the atomic mass. Atomic mass is simply the mass of one atom of carbon. Turns out, if you take that mass of one atom of carbon and you convert it into grams, so that means if you take one atom of carbon, you multiply it by this, you would get 12.01 grams. So if you can take the atomic mass directly, put a grams after it, and you have the mass of Avogadro's number of carbon atoms. Okay? Turns out, when you do that, now when you attach the grams to it, this thing is called the molar mass of carbon. So it's very simple. If you want to find the molar mass of any element in the periodic table, just look at the atomic mass and put a G after the atomic mass, grams. So the molar mass of hydrogen would be 1.001 grams. The molar mass of oxygen would be 16.000 grams. Now, key point of difference out here, when we talk about atomic masses, we're talking about the mass of one atom. When we talk about molar masses, we're talking about the mass of 1 mole of atoms, which is Avogadro's number of 6.022 times 10 to the power 23 number of atoms. Let's go ahead and practice a few of these. So let's say you have to calculate the molar mass. So let's write this down. Calculate the molar mass of 1 oxygen. Now notice carefully, oxygen, that is a diatomic molecule. There are 2 atoms of oxygen in that one molecule. So all you will do is look at the periodic table. I strongly urge you to pause this video, take out the periodic table, look at the periodic table to find the atomic mass of oxygen, and that will be the same as the molar mass. So depending upon the periodic table you're looking at, you may come across a number which is 15.99, or you might come across something that says 16.00. Doesn't matter, let's go with a 15.99. Now that is for 1 oxygen, but there are 2. So you will multiply this with 2, and that is going to give you a number which is 31.98 grams. Okay, let's do another one. Let's say you have to find the molar mass of this molecule, Fe2O3. So there's 2 irons and 3 oxygens. Okay, so all you have to do is look up iron first, which is 55.845. You have 2 of them, so we multiply that by 2, plus you have 3 oxygens, and we know oxygen is already 15.99, so 3 times 15.99, and then just go ahead and let your calculator do the rest. So I'm going to take my calculator out here and do that. So this entire thing, and remove the equal to sign, this thing comes out to be 111.69, and this one is 3 times 15.99, which is 47.97. Go ahead and add them together, and I get 159.66. You can correct for significant figures out here. Typically, rule of thumb is you should carry anything from the periodic table, carry to 2 decimal places, and then you can correct for significant figures eventually. So it turns out you started off with 4 significant figures, which is the least number out here, and you're sticking with 2 decimal places out here when you add them. So really, when your rules of addition say you stick with the same number of decimal places, so that's 159.666 is the correct number of significant figures, so that's grams per mole. Notice carefully how I wrote grams. We're trying to calculate the molar mass, so really that these many grams is the mass of 1 mole of Fe2O3 molecules. Now oftentimes you'll come across many problems where quantities are given to you in grams, and then you have to somehow calculate it in moles. Sometimes the quantity will be given to you in grams. You have to calculate the number of atoms of something. So it's important to know the relationship between this and to be able to go quickly back and forth between grams, moles, and number of atoms or molecules and so on. So let me show you a quick way to go back and forth. So when you have grams of something, if you want to convert to moles, you have to divide by the molar mass of whatever species you're trying to convert. Conversely, if you're trying to go from moles back to grams, then you have to multiply with the molar mass. And now when you're trying to go from moles to number of atoms, molecules, ions, whatever, so number of units, then you want to multiply with Avogadro's number. And if you're going from number of units back to moles, you want to divide by Avogadro's number. And you might recall Avogadro's number is 6.022 times 10 to the 23. Okay. Now, really important out here, you cannot go from grams directly to number of units. You have to go through moles. Conversely, you cannot go from number of units directly to grams. You have to go through moles. So if you remember this conversion, let's say conversion chart, then you can easily go back and forth without any problems. Okay, I'm just going to box this. I highly recommend you pause the video and write this down. So let's say you have to calculate. I'm going to go ahead and write a problem out here. And the question is, what is the mass of 1.33 moles of titanium? That's the question. They're asking you what's the mass of 1.33 moles of titanium, which means moles is given to you. So you're at this step, this chart. And they're asking you what's the mass, which means they're asking you for grams. So you have to go from moles to grams. Okay. To go from moles to grams, you need the molar mass. So your first job is to find out what's the symbol of titanium, which is Ti, and then look at the periodic table to find out what is the molar mass of titanium. That's what I'm going to do now. So it turns out titanium is 47.867 grams per mole. That's the molar mass of titanium. So according to this, if I'm going from moles to grams, I have to go down this way. Watch the arrow. So I take the moles, I multiply it with the molar mass, and that should give me the grams. Okay. So let's go ahead and do that. 1.33 moles titanium times the molar mass, which is 47.867 grams over moles. Notice, see how the moles cancel out? So I'll be left with grams of titanium, which is equal to 63.66 grams. Okay. Check for significant figures out here. Since you were given 1.33, there's too many significant figures out here. You want to reduce that by 1, so we're going to round the 6 to 7. So the answer should be 63.7 grams. Let's take a look at this problem where the question gives you 2.55 times 10 to the 23 atoms of lead, and they're asking you for the mass. So you're going from number of atoms, so that's number of atoms, to grams, which means you're going from here to moles and moles to grams. So to go from number of units to moles, you need Avogadro's number, right? So you're going downwards out here. So you take the number of atoms of lead, and you got to divide by Avogadro's number first. So let's do that. Okay. So 2.55 times 10 to the 23 atoms of, the symbol of lead is Pb. I'm going to divide that by Avogadro's number, which is 6.022 times 10 to the 23. This entire thing should actually give me moles. Okay. So just so that you know, these many units is equal to 1 mole, right? So this is really over mole if you really want to times 1 over mole. If you really want to, or let's put it this way, this is really atoms over moles. So that way the atoms cancel out and you're left with moles on top. Anyway, so whatever, you don't have to solve this part right now. Right now, we just need to know that whatever we get from this is moles. Now to go from moles to grams, we need the molar mass of lead, and we're going this way. So whatever moles we get from here, we're going to multiply with the molar mass. So let's look at the periodic table and find the molar mass of lead. So it turns out the molar mass of lead is 207.2 grams per mole. Don't forget to put the proper units. And then this mole cancels out with that. And eventually, when you solve all of this, you will get the, the mass of lead, because what we left is grams. So let's go ahead and do that. So that gives me 87.74 grams of lead. Now let's check for significant figures. 3 significant figures out here were given to us, so we have to round to 3 significant figures, so we have to stop here. 87.7 grams of lead. A little note on significant figures. Oftentimes you might have learned about significant figures long time back, and you might forget to make that correction. If you are inputting your answer into the book, into some software or anything like that, and you put this as your answer, you will not get points for that answer simply because you haven't rounded to the correct number of significant figures. So you lose all the points for all the hard work you did. So make sure you make significant figures your friend, because that's the answer that you need to specify. You have to be very technical out here, okay? And if you've forgotten significant figures, I recommend go and review that. Here's another problem where the question is, what is the mass of a single molecule of sulfur dioxide, okay? So they're starting with a single molecule. So number of units is what the question is starting with. It's asking you to go from a single molecule right up to grams, the mass, okay? Now there are a couple of things you need to figure out here. Number one is, what does sulfur dioxide look like? What's the formula? If you recall how to write formulas from names, then you'll see that sulfur dioxide is actually SO2, okay? Again, if you've forgotten how to write formulas from names, you might want to go back and refresh that part of your chemistry, okay? So there it is, SO2. Okay, so you're going from a single molecule. So the first thing we need is Avogadro's number. So we're going to take that one, the mass of a single molecule. So we're going to take the single, so 1, and we're going to divide it by Avogadro's number. So 1 molecule of sulfur dioxide divided by 6.022 times 10 to the 23. That's going to be molecules per mole, right? Okay, so molecules cancels out. What we get would be moles. And then you have to go from moles to grams, so we have to divide by the molar mass. So let's go ahead and calculate the molar mass of sulfur dioxide. Here's where you go back to your periodic table. So it turns out sulfur is 32.08 grams and oxygen is 15.99, and you have 2 oxygens, so we're going to multiply that by 2, okay? So that gives me a total of 64.08 grams per mole. That's the molar mass of, sorry, that's 64.06 grams per mole, okay? So now that we have that, we're going to multiply that molar mass by the moles that we got out here. So times 64.06 grams per mole. And then whatever we get would be the answer. So this gives me 10.64 times 10 to the negative 23 grams. Okay, let's make that, express that in proper scientific notation. So if you move the decimal one place this way, that's going to be 1.064. Now since we moved the decimal this way, this number got smaller, which means we got to multiply this by a factor of 10 to make it bigger. So times 10 to the minus 22 grams. Okay, now let's check for significant figures. So single molecule of sulfur dioxide, that's the molar mass. So yeah, so that's the correct number of significant figures. Okay, here's another problem. How many oxygen atoms are in 3 moles of Li2SO4? Okay, so first of all, they're asking you for how many oxygen atoms, which means you're trying to go to number of units, and then they're giving you moles, so they're giving you moles, the number of units. Okay, so before you can find out the oxygen atoms, you have to find out how many units of Li2SO4 are in these many moles. Okay, so let's do that first. So let's kind of break this down a little bit. How many units of Li2SO4 in 3 moles. Okay, so to answer this question, all I'm going to do is take the moles, 3 moles, and I'm going to multiply by Avogadro's number to get the number of units. So times 6.022 times 10 to the 23 units. So per mole, of course. That's going to give me the number of units, which happens to be 18.07 times 10 to the 23 units of Li2SO4. So you can think of this as molecules of Li2SO4. All right. Now that we have these many molecules, now look at it. Within each molecule, how many oxygen atoms are there? Within one of them, there's actually 4. So if there are these many, the number of oxygen atoms is going to be 4 times these many. So number of oxygen atoms is equal to 4 times 18.07 times 10 to the 23, which is equal to 72.26 times 10 to the 23 atoms. There you have it. I hope these 4 problems kind of made sense in terms of how to use this relationship. You will see this relationship pop up in many options and many situations, and you just have to kind of rely on it. So my recommendation would be to practice this quite a lot.